The second subunit focuses on studying the exposome. One of the earliest modern exposome investigations examined exposure to asbestos. Some of the earliest suspicions regarding the negative health consequences of asbestos and its link to cancer date back to the 1930s. Officially, the link between asbestos and lung cancer was established in 1955 by Richard Dahl, and this was later confirmed by several epidemiological studies. Another example of exposome research is likely quite familiar to you. In 1952, Hammond and Horn completed a 3-year study establishing the link between cigarette smoking and both heart disease and, of course, lung cancer. The study of the exposome can be approached in two general ways. The first is a bottom-up approach, where investigators seek to identify the potential for external exposures by measuring, for example, chemicals in the air, water, and food. Alternatively, the exposome can be studied in a top-down manner, in which we seek to identify evidence of exposure burden within an individual. In other words, chemicals or quantities of chemicals or materials outside what is likely to be expected within a healthy body. Yet another way to consider and study exposure is by examining the environments we build for ourselves to live and work in, as well as the specific health risks of these contained environments. In order to study an exposome, you first need to be able to measure it. Of course, collecting exposure data accurately is much more difficult than, for example, collecting genetic data. Often we may have to rely on estimates of the likelihood of any exposure and/or the duration of exposure. This figure illustrates some of the strategies that researchers have utilized to try and measure different exposures. This can include questionnaires to learn about an individual's past, including residency, occupation, and medical history. It's also possible to use geographic information systems, or GIS, to generate environmental models of exposure with respect to things like air pollution, noise, etc. Information could also be gleaned from an individual's pictures to gain information about cosmetic use, diet, or possibly the use of cleaning products. Mobile devices could be leveraged to gain additional information with respect to where an individual travels or spends time, or to monitor other exposures that can be captured easily from these devices. Also, in the clinic, we can examine top-down exposome information by analyzing biomarkers from biomedical samples, including urine and blood. Further, if you want to examine the indirect effects of exposures, we can also utilize other omics technologies to gather evidence of those exposures' impact on the internal environment. Let's spend a little time now looking at some of these technologies for exposure assessment. From biomedical samples taken in a clinic, we could, for example, measure the burden of toxins within an individual. Such toxins might include heavy metals like mercury, lead, arsenic, or cadmium. Also could include chlorinated pesticides, organophosphate pesticides, PBCs, or volatile organic solvents. Certain basic exposure information can be obtained using small physical home monitoring devices applied as local sensors. These technologies are typically specific to measuring one or a small handful of exposure types. Here is an example of a small sensor called NetAtmo that measures temperature, humidity, noise, and carbon dioxide. As suggested previously, smartphone applications provide a low-hanging fruit strategy to gather additional exposure information utilizing the built-in features of the phone, as well as cleverly designed applications. Some existing phone apps for measuring exposure include noise exposure, electromagnetic field or EMF, diet tracking, and cosmic radiation, such as the Track Your Dose app. One way to extend the ability of smartphones to collect data is to pair them with other wearable technologies. One example of this is the well-known Fitbit for activity monitoring. But there are other wearable devices that can, for example, measure air quality or UV exposure. As previously suggested, it's impractical, if not impossible, to measure all lifetime exposures. A more practical strategy is for scientists to focus initially on classes of substances known to be biologically active, and therefore likely to cause some sort of negative health impact. For example, this could include reactive electrophiles, persistent organic compounds, metals, and metabolites. Ultimately, it's most practical to focus on specific local exposomes with respect to a single target health outcome. An example of a more focused exposome research program includes the Helix Early Life Exposome Study, which seeks to combine all environmental hazards that mothers and children are exposed to, and linking this to the health, growth, and development of children. More specifically, this program looks to measure a range of chemical and physical environmental hazards in food, consumer products, water, air, noise, and the built environment in pre- and postnatal early life periods. It also seeks to quantify uncertainty in exposure estimates. It also seeks to determine the molecular profiles and biological pathways associated with multiple exposures. And it seeks to estimate the burden of childhood disease in Europe due to multiple environmental exposures. Another example of a targeted exposome study focuses on exposures believed to impact skin aging. We see here factors such as pollution, sun exposure, tobacco, temperature, all as being likely factors for impacting skin aging. One last targeted example examines the social stress exposome, which focuses on social stressors from the home or neighborhood, including parenting, social relationships, stressful events, trauma, poor nutrition, chemical exposures, exercise, and substance use. Beyond the technical challenges of measuring the exposome and gathering this data in an accurate, representative manner, there are still difficult challenges regarding how this data will be analyzed, along with other omics data sources, to gain a complete picture of the factors that contribute to the occurrence of different health outcomes. This figure summarizes some of these challenges and illustrates the often poorly understood connection between genome, exposome, and the collection of health outcomes that we will refer to here as the phenome. One of the most fundamental analytical challenges is to determine what variables causally contribute to the health outcomes that we want to understand. In particular, many additional variables might be correlated with outcome, making it difficult to identify which variables are causal of the health outcome versus which are simply associated with that health outcome. Ultimately, the goals of these studies are to establish causality so that proper preventative measures and treatments can be identified. This concludes our second subunit that is focused on studying the exposome.